What I want to talk about this morning is code as risk. And we'll kind of walk into this topic gently and carefully. So I'm Kevlin Henney, and a number of years ago edited this particular book, 97 Things Every Programmer Should Know. And during lockdown, finished editing along with Trisha G, this book, 97 Things Every Java Programmer Should Know. But I also have an interest not just in the detail, but in the larger scale of how things are put together, the software architecture and kind of our vision of how this works. But my name is sometimes more associated with something else. And that something else is, well, it's captured by this piece from the Register from about 2 years ago. There at the end, made 3 Kevlin Henneys at Waterloo Station, where the definition is provided. Kevlin Henney is a humiliating public software failure, photographed and tweeted to the eponymous account. Kevlin Henneys are frequently seen at ATM machines, supermarket checkouts, but the best ones usually occur in transport hubs where they enjoy the full benefit of giant displays, such as this one. Now, this is kind of one of the places where it all started. I used to take, the minute that we got cameras with our phones, I started taking photographs of failures of software in public places. And this one was taken at Madrid Airport, Terminal 1, if I recall correctly, back in 2006. And what intrigued me, and this is actually a part of a DOS-based stack. So 2006, Madrid Airport is using DOS for its operating system, for its displays. And for most people, they're just wondering what on earth this is. It's not an advertisement. And everybody's looking at this kind of like 5 free packets. 5 free packets. Where can I get my free packets? Because everybody clues into the word free. But this error screen was enormous. I mean, it actually took me 2 photographs to get it. But I'd started around that time just grabbing screenshots, taking photographs. Because for me, it is interesting that we see software in its failed form. It turns out that software developers are the largest installers of accidental installation art on the planet. We create art. It is everywhere. It's not intentional, but it's there. We can do it on your browser. We can do it on your mobile. We can do it in public spaces. And this failure, this failure is interesting, but more interesting because we see how something is built. Because when something fails, it fractures along particular lines that show you its structure. I just mentioned that this was an additional DOS stack on the previous one. This one, you can tell how old this is. It's Mozilla, so not even Firefox. It's pre-Chrome. And this is the Dutch website for the Dutch rail network, NS. And I was going to see a friend back in the days when we could travel, and I wanted to arrive at his place earlier. Apparently there is no earlier. There is only java.lang.null pointer exception. Here we see that the underlying system is built in Java. We also see that there is not a big outer try catch that should have caught this and commuted it to some simpler error, such as, hey, things aren't working right now, in English or in Dutch, but definitely not in Java. So what we're seeing is an interesting example of failure that reveals something about the system. But we can go further, because how did this get through? How was this not tested? Was this a scenario that nobody had thought of? Maybe it tells us that the team were rushed or not familiar with the techniques that they were using in the frameworks. Now, what is interesting here is that I presented this at a conference in the Netherlands a couple of years later, and somebody came up to me, after laughing, of course, somebody came up to me afterwards and said, you know, they still have that bug. And this kind of makes you wonder something else. That bug was there for nearly 2 years, and it was widely known in the Netherlands. What development process or management process was causing problems here? Because clearly that was an obstacle. That was something that was getting in the way. More recently with NS, I had this one. His email is not a valid ticket. That's fine, but my order number is apparently null. At this point, we get the sense that this might well have been written in JavaScript. This one was sent to me by someone in Canada, and it turns out that it is not simply bilingual, English and French. It is trilingual, PHP as well. And we also see the object model being revealed here. And so back in 2016, there was a slight shift in the fact people started actually tweeting these to me, because I used to use these images within talks and when I'm running workshops. And I have an interest in testing, and people started tweeting these at me. And it got to the point where in 2016, Tagline then put this: arriving in Bologna, I saw a Kevlin Henney screen. Whilst queuing to leave, right, a Kevlin Henney screen. And here we see another: you're never safe from a Kevlin Henney. So it's even made its way into the Urban Dictionary, apparently. This is a couple of years ago. A software failure that happens in some public space. Oh, look, the bus monitor just pulled a Kevlin Henney. Now, what I find interesting here is that it says, get a Kevlin Henney mug. My wife, when I showed this to my wife, she said, no, it's fine, I've already got one. But there's a serious side to this. This is entertaining at one level, and I retweet these on my Twitter stream, although sometimes I get sent these privately. There is another point to this. That point that is of interest. By the way, some of the companies do actually pick up on these and start asking questions. Oh, which station was this, or where was this reported? But what we're seeing here is examples where we understand the nature of the system. We see its internal structure. So I think this was the Waldorf Hilton in London, and we can see pretty much, if you want to find out, we've got a beautiful manifest here of WebLogic, use of Spring Framework, and so on. We can see how the system is structured. These things are just errors. But the difference for a user between an error and a security breach is minimal, because these actually have a huge overlap. The scope for error tells us there is something wrong with our software. If there is something wrong, then there is something that somebody else can exploit. So we see that this is not simply a case of bugs. The vivid example a couple of years back of the WannaCry ransomware made that very, very apparent, attacking a lot of public services globally. And this is something that's not been going away. A couple of years back, there was also the Mambo ransomware. We saw also last year this interesting report. Nearly 3 weeks, Baltimore has struggled with a cyber attack by digital extortionists. What frustrated city employees and residents do not know, a key component of the malware that the cyber criminals were using was developed at taxpayer expense, a short drive down the Baltimore-Washington Parkway at the NSA. It turns out that the software that the NSA used to hack other countries is out in the wild and is being used. So we need to get a grip on this one. This is not just simply a case of error modes, it's also security modes, the liability of software, or rather the liability of code. So let's break this one down. Let's have an initial look. Let's go and raid the dictionary, see what wisdom the dictionary has to offer us. So code as a noun, the one we're familiar with, a set of instructions for a computer. But actually we don't really program at this level. We tend to consider our programs to be slightly higher level. We think in terms of programs and applications. We also find that the word code is used elsewhere. Code breaker, for example, a system of words, figures, or symbols used to represent others. So we encode things, especially for the purposes of secrecy. And we find this with technical debt. We find this this indebtedness, we find this challenge sometimes, that when we look at our code, it seems to be written in code. It is difficult to decrypt. And then we have another set of ideas, the idea of a set of conventions, like a code of practice. But this talk title is Code as Risk. So let's talk about the risk side of things. What is risk? There's a number of definitions. Situation involving exposure to danger. The chance or hazard of commercial loss. Notice here there is this idea of probability, but it's two aspects. It's your exposure to the probability, the product of the consequence and the probability of a hazardous event or phenomenon. More formally, exposure to a proposition of which one is uncertain. So in other words, risk is not simply something that is bad. It is not simply something that has a probability. It is being exposed to that. It is what is the probability terrible things happen. So let's understand what the nature of this thing is, because we often think of code as merely an artifact, a construction artifact. And for many years, I pushed the view that code is an asset. And that is still true. It's something you should value. But at the same time, there is another truth that Kirk Pepperdine and I elaborated. It turns out 12 years ago. I thought it was about 10 years ago, but I found an earlier tweet when I was not on Twitter and when Kirk couldn't spell my name. Interesting conversation with Kevlin Henney. Outcome, functionality is an asset, code is a liability. That's the thing. Code is the thing that prevents us from doing the thing that we want to do in our software. It is also the thing that enables it. But when you imagine the thing that you're going to work on, you say, okay, imagine it. Okay, I'm done. Except you're not done. You've only just begun. You now actually have to do this. What is the thing that is holding you back from putting the functionality in? What is the thing that is preventing you from getting the idea right? It's code. It's all the code that's already there. It's the code that you now need to express. In other words, this insight is important because it tells you that if code is a liability, it doesn't mean it's intrinsically bad. It just means you need to manage it. You need to keep your eyes on it. You need to understand it. It also gives us a very strong case. We were arguing by Twitter of what I call decremental development, which is an idea I came up with about 15 years ago. The idea is that we are often talking about incremental approaches as opposed to big bang approaches. But the thing we also need to appreciate is the other side of it, the decremental side, the idea that we need to reduce the stuff, reduce our exposure to this stuff. So given that we have time delays and things like that, let's go to Mars. We'll be going to Mars later in the talk. But I wanted to pick from something, a talk and a really nice piece by Gerald Holtzman, who headed up the APL that wrote the software for the Mars Curiosity rover. And for those that are curious, the Mars Curiosity rover is written, the software for that is written using C99. And also a whole level of static analysis. And actually how they do this is really quite interesting. And a lot of projects could learn a great deal from the techniques that they use to improve their quality. But one of the things I loved about the original article Holtzman wrote was he makes this observation: there are standard precautions that can help reduce risk in complex software systems. In other words, there is this really key idea. Risk is the thing that we need to watch out for. A lot of people talk about value. I think that's fine, but you really need to be focusing on risk. Value is the thing that you want. Risk is the thing that will take it away. And so we really need to, it turns out that fortunes can change overnight, reputations can be destroyed and all the rest of it, and you can frustrate your users either through accidental outages or by giving somebody else an opportunity to insert themselves into your system. But as well, we'll frustrate users and our customers by not being able to deliver the stuff that we care about or they care about. All of these things come out of the code. But here's what he said. This includes the definition of a good software architecture based on a clean separation of concerns, data hiding, modularity, well-defined interfaces, and strong fault protection mechanisms. That's 5 things. Separation of concerns and data hiding and well-defined interfaces are 1970s. Modularity is a concept from the 1960s, but was better expressed in the 1970s. Strong fault protection mechanisms, clearly that's not necessarily applicable to every class of system. But if you have a probe on Mars, then you need strong fault protection mechanisms. So of these 5, well, obviously, let's put it this way. What happens if there's a crash? You can't just simply restart it. You know, this is not some kind of cloud server. This is not simply reboot my phone. This is not a case of send Matt Damon out to fix it or something like that. You need strong fault protection mechanisms. But with that exception, 4 of these ideas are from the 1970s. We're here 50 years later. How well are we doing? There's not a new idea that we have yet to apply that will make a difference. Okay, we need to just apply the old ideas. Now, the guy I mentioned about modularity, the guy who pretty much put modularity on the map, as I say, it was an idea in the late 60s, but really how we thought about it was this guy, David Parnas. And he talked about dependencies as well. And one of the things I think is important is I think a lot of people sort of talk about dependencies in a very casual way. They assume that the dependencies they've got, they're looking at their piece of code and they're thinking, right, the dependencies are the things that I can see in the code here. It's code calling code, it's code bringing in code, and that's it. And that's what I need to manage. And it's like, no, that's not it. Or rather, that's not all of it. The connections between modules are the assumptions which the modules make about each other. It turns out your dependency structure is a lot bigger than you think it is. So if we imagine that we have, here is our software system, here is the package or subsystem or piece of code of interest. Normally when we talk about dependencies, we'll say, oh, here's the other pieces of code that I care about. But ultimately, we own this code. This is inside our boundary of control. And then there's the other stuff we just reuse. And it's kind of interesting because it's like that's towards the horizon. It's as if we don't see it. It's out of the corner of our vision. It's like, oh yeah, we're using that person's library. We're just reusing it. And yet we don't count that as a proper dependency. Oh, it's something to be loaded, but we don't evaluate it. When I ask people about these, I say, what control do you have over it? Well, we don't. It's a third party. What dependencies does it use? Oh, it's okay, the tool gets those. No, that's not okay at all. You mean that your whole product depends on stuff you have no idea about. That's a risk. That's a huge risk. People normally care about this stuff. They forget about the things that they're pulling in, pull in. And then they forget about the platform. The programming languages. I ran this exercise at a company. I was doing a consultancy trip about a year and a half ago. And I said, okay, so tell me about your dependency structure and tell me about the structure of your system. And they listed off everything. And I said, well, you've not put any programming languages in. Oh, that's just implementation details. And I said, well, no, it isn't. It's the reason your system exists. Programming language is not an implementation detail. Without the programming language, there is no system. It's not a detail. It's one of the most important things. So then they put up C++, Java, Python. And I said, well, you haven't listed the version numbers. Oh, well, why does that matter? And I said, well, Python 2 is going out of support. Which version of C++ tells me a little bit about the compiler, which version of Java tells me about the tools you can and can't use. It turns out that your dependencies include all of these things because you do not control them. Now, a lot of people think this is a lot to worry about. You know what? They're right. You should be worried about it because this is about the viability of your product. Your operating system matters. One of the things I've learned through all of these failure screens is the amount of software out there that is running operating systems that are not being supported, is running code base or is running against third-party software whose companies no longer exist. This is something you should be caring about. It's not just the icing on the cake, the value bit that everybody keeps talking about. It's the whole stack. You call yourself a full stack developer, feel free to use that title, but if you can't tell me about your deep dependency structure, oh yeah, when it's deep, it's also deep the other way. Your deep dependency structure is also your market. You have a dependency on your market. You have a dependency on governance, the rules of the domain, the requirements. This is what your dependency diagram looks like. It's not just importing a few modules. And if you are importing modules, watch out, because this is the blind spot. So 4 years ago, we had the left pad incident. This was an interesting one. Just a few lines of code were pulled from a website for a dispute over licensing. And it turns out that lots of people had a transitive dependency on this code, a handful of lines of JavaScript. And the point is that people will happily take on all kinds of stuff. You wouldn't believe some of the stuff that you can find on NPM. It's shocking. I don't mean shocking it's bad. It's just the stuff that people are actually doing. Here's the original left pad. It's not the greatest code. I'll be free to freely admit that. We should always thank people if they are offering open source, but that doesn't mean that what they're offering is necessarily good. It's an act of generosity. It doesn't mean it's intrinsically a good piece of code. This is not great JavaScript code by any stretch of the imagination. I can see a number of issues with it. When I look at this code, I wouldn't want to use it. It doesn't give me confidence. It doesn't look like the person is comfortable with JavaScript or indeed algorithms. But the thing that really worries me is that this is a trivial task. We are padding a string, and yet people don't know how to pad strings, so they pull this in. And when this was pulled, a number of sites that didn't even know they had a dependency on it went down. This was quickly replaced by something that unfortunately was not better. This shows There's a lot of issues with this code. I won't code review this now, but it is not as good as the previous version. I had a go at doing this. You can do it. I'm not a JavaScript programmer. I managed to do it in less, with less code. But here's the thing. Here's the thing that I did. I ran some tests on it. Here are the tests. This is what it looks like when it passes. These are all green. The tests are very simple. I'm not going to really spend time on looking at these. What I do want to emphasize, though, is what we're looking at is a very simple reality checking testing framework where I have named the proposition or the property of the code that I'm interested in, and I have a simple expression that simply demonstrates that. It's just a reality check. It's a hand-rolled testing framework. There you go. That's it on screen. That's all that's needed in the testing framework. And when I run it, I get green. What was interesting is when I ran it against the two previous versions of LeftPad, the original and the replacement, is it fails. It actually turns out that this code that everybody was sharing that caused so many problems had not been tested. It fails in a few well-defined circumstances. It's not a very good padding algorithm either, and yet everybody's using it. So this kind of tells you that if you're going to start using it, it's like having continuous integration, continuous deployment. You can't do that without testing. And the idea of using somebody else's code that has not been tested is something that we should be cautious about. Just because somebody's offered it, it's kind and generous, doesn't mean it's good. So Neil Ford 10 years ago wrote this piece, "Testing is the engineering rigor of software development." That's what makes it real. That's what turns it from something that is some abstract cottage craft into something that is real and durable and people should expect to rely on. It reduces risk. Now, here was another interesting thing. Let's not talk about how you're supposed to package up your modules before you do this. You shouldn't dynamically load things off the web, although there are some very interesting things to say about that. So from NPM, there was this tweet. Glory was at NPM. LeftPad 3, unpublished, breaking lots of builds. To fix, we are unpublishing it at the request of the new owner. Now, this is interesting. We have just pushed back a piece of code. We can push back any piece of code. And it turns out, instead of doing this, we could have easily injected our own code. This is one of the most interesting things about dynamic dependencies that you don't manage. They are dangerous. You need to watch out. And we all often talk about sanitizing the inputs. Your dependencies are your inputs. You don't want to go, you need to sanitize those, either dynamically at runtime, constant runtime checking, but also at build time. Okay, you need to sanitize your inputs. Your dependencies are your inputs. That's how you reduce the risk. Now, the classic one on this one is the XKCD cartoon. "Hi, this is your son's school. We're having some computer trouble." Oh dear, did we break something? In a way. "Did you really name your son blah, blah, blah? Oh yes, little Bobby Tables we call him. Well, we've lost this year's student records. I hope you're happy. And I hope you learn to sanitize your database inputs." This tells us that every escape is an entrance. Every piece of escape code, this is for whether it's SQL injection, whether it's cross-site scripting attacks, whether it's buffer overruns through the use of printf and C libraries. We need to be really careful with this stuff. You need to guard this stuff. And those external dependencies are part of your dependency set. They deserve that. Now, what's interesting about Little is just last week in the UK, Companies House, the place where people register their companies, forced a company to change their name because that name could be used to hack websites. It wasn't actually a fault at Companies House. Their code was absolutely fine. It's just that they were concerned that it turns out this company name could be used by other people on other sites that hadn't sanitized their inputs. So anyway, that company got renamed to this. So this tells us something about our practices. Now, how good are we at practicing or at our practice and understanding the state of the art? If we start saying, well, we have a sense of engineering, then what is engineering? It is the understanding of things that work, things that we know have worked and applying them again. It's simply building up a discipline, a system of knowledge that we rely on. So back to XKCD. I could restructure the program's flow or use one little go-to instead. Yeah, screw good practice. How bad can it be? That's go-to. How bad could it be? 6 years ago, we were hit with a couple of SSL-related security breaches, both of which came from bugs. You see, there's a very strong relationship between bug and security issue. And this was written up, and it's really nice. It's a long piece, but if you have a long build, definitely I recommend looking at this one by Mike Bland, formerly of Google. Go to fail, Heartbleed, and unit testing culture. And the one I'm going to focus on here is, and he shows you the issue. And then a lot of people go, oh, well, this code is written in C. We don't have to unit test it. You can't unit test C. Well, you can. I'm actually running something on that later this month. But he also highlights how to do it. But here's the code. Here's the offending code and why this is called go to fail. This is in Apple's code. And we see here what we have. Oh, well, that doesn't have the right behavior. This is an example of copy and paste code. So, I mean, yeah, using the go to was a bad move. But it's not intrinsically just about the go to. Go-tos invalidate the high-level structure of your program. It's why we don't like them in programming languages. They also make control flow less efficient. Modern optimizers are not very comfortable with them. They're not very comfortable with things like break and other things as well. They stand in the way of refactoring. There's a whole load of reasons why we don't want to do that. And if you've never programmed in a language where the culture was to use go-to, you probably don't understand why it is such a big deal. And if anybody tells you, oh, this is how you normally do it in C, I was a C programmer. No, you don't. This is the stuff we told people not to do. But there's something deeper here. Copy and paste code. There's use of go-to. There's copy and paste code. This is a thing that is picked up by most standard linters. So clearly there was no static analysis going on, and there were no tests. In other words, this is a perfect storm. Have we not learnt yet that this is what we do? As Mike Bland says, these bugs are as instructive as they were devastating. They were rooted in the same programmer optimism. It can't happen to me. Overconfidence and haste that strike projects of all sizes and domains. These bugs arouse my passion because I've seen and lived the benefits of unit testing, and this strongly imprinted experience compels me to reflect on how unit testing approaches could prevent defects as high impact and high profile as these SSL bugs. So I said we were going to Mars. Let's go to Mars. Again, 2016, October 2016. We've moved to October 2016. It was March when we last were in 2016. That was GLEFPAD. Here we are going to land on Mars. The Schiaparelli lander, part of the European Space Agency's mission to Mars, part of the ExoMars mission. It's going to land on the surface. However, things did not go well. Schiaparelli's internal measurement unit went about its business of calculating the lander's rotation rate. So we've just entered the atmosphere, and you rotate a craft, it gives it stability. So you're rotating the craft as you enter, and that's great. For some reason, the IMU calculated a saturation maximum period that persisted for 1 second longer than what would normally be expected at this stage. Whatever the reasons for that, all we need to know is, it took a bit longer. What happens to that information? When the IMU sent this bogus information to the craft's navigation system, it calculated a negative altitude. In other words, instead of being above ground, it thought it was below ground. Now, one of the great things about the European Space Agency is that it will publish its inquiries. So here's the inquiry. By the way, good use of vocabulary, Schiaparelli anomaly inquiry. If you have anything disastrous happen at work, feel free to use the word anomaly. It's lovely and understated. It's an anomaly. It's not a horrendous crash. It's an anomaly. Because of the error in the estimated attitude that occurred at parachute inflation. So this is where it all comes from. When you're entering the atmosphere, it's wobbling. And there's a lot of wobble. And put simply, what was supposed to happen is that you're supposed to measure the wobble. Half a degree here, half a degree there. Now that should cancel out. If I go half a degree up and then half a degree down on this side, that should be 0. Unfortunately, it accumulated half a degree plus another half degree. That's 1 degree plus another half degree, and so on. It accumulated rather than being a balance. Erroneous off vertical angle and deduced a negative altitude. Cosine of angles greater than 90 degrees are negative. Now that's an interesting statement. Why are we suddenly teaching people school maths? So let's understand this. Cosine of the off vertical angle, in other words, how far off vertical it was. You want your craft to be like this, and apparently we are actually almost upside down. So what are we saying? Cosine of off vertical is greater than or equal to 0 is what we are assuming. We have assumed this is the case. Actually, specifically, we've assumed that the off vertical angle is less than or equal to 90 degrees. Therefore, the cosine is greater than or equal to 0. And if you're feeling a little more mathematical, if you come from a mathematical discipline, you'd probably rather write that as half pi. So notice what we've written here. There is an assumption. Assumptions are invisible. Assumptions are kind of a form of knowledge that is like Lego bricks in the dark. You don't know they're there until you step on them. Or even if you know that they might be there, you don't know where they are. Every time you enter a piece of work, every time you undertake a project, you have assumptions. You don't know what they are yet. You know some, you can see some. The Lego bricks by the door, based on experience from other projects and insights you and your colleagues might have. But there's a whole load of other things there that you will not know until you have stepped barefoot on those things. So we have an assumption. At that point, you discover you have an assumption, normally when it's violated. So let's reframe this in a more formal computer science way. Precondition and postcondition. In fact, we can be much more formal about it. We can say precondition, action, postcondition. This is the kind of formalism that's used to that Tony Hoare in the late 1960s, again, no new ideas, talked about and gave rise to things like programming by contract in the late 1980s as an idea. The idea of precondition, method call, postcondition. So here is what we've got. We also see that it is identical and transfers directly over to given, when, then, if you're familiar with BDD. And this gives us a test structure, arrange, act, assert. These are all the same idea. There's only one idea here. But let's put this from another point of view. What was the problem we encountered? If we were to write this one out, because I want this to be fault tolerant, I would have said, if the angle is less than that, then we're going to calculate the off vertical, using the off vertical. Otherwise, what are we going to do? We haven't got a behavior for that. We just did this. So what happened is that this fateful miscalculation set off a cascade of despair. Again, terminology you might want to consider using in your own company. Cascade of despair, lovely piece of English. Triggering the premature release of the parachute and the back shell. In other words, Schiaparelli, as it descended, suddenly thought, oh my goodness, I'm already on the ground, but I'm fully dressed. So let's get rid of all the stuff that I use for landing. And brief firing of the braking thrusters and activation of the on-ground systems, as if Schiaparelli had already reached the surface. Sadly, this all happened while the vehicle was still 3,700 meters above the ground. And Mars's gravity may be lower than Earth's, but 4K is still a drop. And the crash site was visible from orbit, from the ExoMars orbiter. So what do we learn from this? It's a failure of failure handling. It's an assumption. It's a gap. And a paper in 2014 highlighted a number of things by looking at open source distributed data intensive systems with a very simple conclusion, which is in its title. Simple testing can prevent most critical failures. The observation that almost all catastrophic failures are the result of incorrect handling of non-fatal errors explicitly signaled in the software. So majority of the production failures can be reproduced by a unit test. That's about 3/4 of them. So whenever we say, oh, well, we can't unit test everything, it's true. But we can reproduce most of the problems we encounter. And the benefit of doing so is we cannot always do it in advance. But when we have found something, we should be putting this one in to reduce the risk in subsequent releases. In other words, don't just fix a bug. Write a test that shows you fixed the bug. And therefore you have an audit trail and a trail of credibility, but also a trail of risk reduction. But when we think about code as risk, we need to expand our view of what we mean by code. So we're going to go forward to 2017 here. And what we see here is a launch of a Soyuz, and the headline for this one was Soyuz fails to deliver 19 satellites from Vostochny, which is in the far, far east of Russia. Most rocket launches from the Russian space agency, Roscosmos, tend to occur in either Plesetsk or in Kazakhstan, in Baikonur. But this one was originally going to be launched from one of these, and these are very much further west. But they relocated the launch site to Vostochny. And it turns out that all the hardware worked. Everything absolutely worked in the first two stages. Almost unbelievably, the flight control system on the frigate did not have the correct settings for the mission originating from the new launch site in Vostochny. It basically had the old configuration. It had the old configuration, which was for launching from way, way west. So when the final stage basically started up, it kind of looking around, going like, good grief, I am half a world away from where I should be. I am way off course. I need to fire a course correction, at which point the code actually worked correctly. And the upper stage was seen re-entering the Earth's atmosphere somewhere around Iceland. It was a British Airways flight that spotted it. So here's the blind spot people have. They think that configuration is not code, but it is. Configuration is code. I said this on Twitter a few months back, and some guy said, oh no, but I don't think it is. I don't care what you think. It doesn't matter. Your opinion on this one is not important. Configuration is code. If you are using JSON as configuration, that should kind of bring it home to you. JSON is a subset of JavaScript. It has a formal syntax. Even if you're using just key value pairs, that is code. It might not be Turing complete, but it is still code. And we have a blind spot. We have a blind spot when it comes to testing this stuff. Another paper from around 2016, early detection of configurations to reduce failure damage. Our study shows many of today's mature, widely used software systems are subject to latent configuration errors in their critically important configurations. We don't test this. We regard configuration as something that is not to do with our code. It merely helps how something runs. No, it defines how it runs. It is part of your code. There is no difference to having that external or internal when you look at it from a runtime point of view in terms of the behavior. So we need to kind of expand our view of what we consider to be code. And perhaps we also need to go against Postal's law. Postal's law is often framed as be conservative in what you do, be liberal in what you accept from others. I think we actually need to take this one slightly differently. Be conservative in what you do, be conservative in what you accept from others. Don't be tolerant of invalid input. Reject it rather than rather than try and add an interpretation to it. We see this problem all the time with spreadsheets, and spreadsheets, it turns out, have had some very life-threatening consequences because of this idea of being liberal in accepting any input without questioning it. This is the key thing. We need to question these things. So at this point, what I'm going to do is I'm going to start heading into the home straight with a simple understanding of how should we look at our systems. I'm going to go back 40 years for this. Meyer Lehman, in his wonderful paper, Programs, Life Cycles, and Laws of Software Evolution, he categorizes 3 different ways of looking at the scope and scale of our systems and their implication. An S program, it's any piece of code that can be formally defined from a specification. In other words, the stuff that you can unit test. The stuff that is sorting algorithms and stuff that is accountancy. Accountancy has well-defined rules. It has a well-defined frame. I can test against this. It has a well-defined idea of correctness. P programs are a little more negotiable. This is where some of our AI stuff fits in. We actually have to work out what we mean by correct. And so therefore, if you have developers developing the code and determining the criteria of correctness, what is suitable, then we have 2 aspects that are slightly slippery with respect to one another. We need to be much more cautious about this. You cannot demonstrate the appropriateness of that system from within that context. You need a market, you need customers, you need external points of view. But the one that's really interesting is when we throw that into the bigger world. When our systems have become part of the world that then feeds our systems. There's a feedback loop. The program has become part of the world it models. It is embedded in it. And most of our stuff these days is E-program class. Back in 1980, less so. So we can see a really simple example of this. And they understand the risks and assumptions here, taken from this example from 2011. So here's a book, The Making of a Fly, The Genetics of Animal Design. Now, honestly, I couldn't tell you anything about this book, except that apparently it goes, if you want the new one, it goes for $1.7 million US. If you want it used, however, $35 is what you'll pay. I have been told by somebody, I showed this slide to somebody who was actually had a PhD in genetics, and he said, yeah, this is pretty much the Bible. This is one of the good books. But nearly $2 million? I don't think that's very likely. Now, you'll notice that there are two sellers in the market. You can't get this straight from Amazon. There's Profnath and there's Bawdy Book. Profnath are offering it for $500,000 cheaper. Well, that's a bargain. Now, what's interesting here is that Michael Eisen observed this over a few days. What he observed was even more interesting. There is a ratio between Profnath and Bawdy Book. It's very precise. It's computationally precise. It turns out that they are both using automated algorithms for pricing. And Profnath has the book, and they are undercutting anybody else out there who also offers the book. They're just a fraction of a percent cheaper. Bawdy Book do not have the book, and what they're doing is they will buy it off somebody else and then offer a 27% markup to sell it back to you. These two algorithms are both individually correct, and they are unchecked. The assumption is that the marketplace does not use this kind of thing, that there are more agents in the marketplace. This assumption is broken. It broke all the way up to, I think, 23 million before they stopped. Now, Amazon have put stuff in place now to stop this kind of thing happening, but we see this kind of thing. This is a flash crash from 2016. That is the pound. Now, obviously, the pound has been having a really hard time of it in recent years because of a rather large and unsuccessful social experiment in the UK. We've been running since 2016. But in October, there was no way you could account for this by human behavior. This kind of crash is optimized. It's algorithmic trading in action. This is the kind of risk that we are running when we do not understand the assumptions and gaps in our thinking. So let's close by considering this idea that from the Finnish architect Eliel Saarinen, always design a thing by considering it in its next larger context. And I'll leave the final word to Maya Lehman. This is 40 years ago. This is very predictive. This is what we need to appreciate now. As mankind relies more and more on the software that controls the computers that in turn guide society, it becomes crucial that people control absolutely the programs and the processes by which they are produced throughout the useful life of the program. Thank you very much.